In astronomy and celestial navigation, an ephemeris gives the positions of naturally occurring astronomical objects as well as artificial satellites in the sky at a given time or times. Historically, positions were given as printed tables of values, given at regular intervals of date and time. Modern ephemerides are often computed electronically from mathematical models of the motion of astronomical objects and the Earth. Even though the calculation of these tables was one of the first applications of mechanical computers, printed ephemerides are still produced, as they are useful when computational devices are not available. The astronomical position calculated from an ephemeris is given in the spherical polar coordinate system of right ascension and declination. Some of the astronomical phenomena of interest to astronomers are eclipses, apparent retrograde motion, planetary stations, planetary ingresses, sidereal time, positions for the mean and true nodes of the Moon, the phases of the Moon, and the positions of minor celestial bodies such as Chiron. Ephemerides are used in celestial navigation, astronomy and astrology. Astrologers typically have different needs than astronomers, for example, the calculation of astrological aspects, and may produce ephemerides specialized to their own field. History. 2nd millennium BC, Panchanga tables based on Jyotisha in the Vedic period of Indian astronomy. 1st millennium BC, ephemerides in Babylonian astronomy. 2nd century AD, the Almagest and the Handi tables of Ptolemy. 8th century AD, the Zij of Ibrahim al-Fazari. 9th century AD, the Zij of Muhammad ibn Musa al-Khwarizmi. 12th century AD, the Tables of Toledo, based largely on Arabic Zij sources of Islamic astronomy, were edited by Gerard of Cremona to form the standard European ephemeris until the Alfonsine tables. 13th century, the Zij-Ilkhani, or Ilkhanic tables, were compiled at the Marighera Observatory in Persia. 13th century, the Alfonsine tables were compiled in Spain to correct anomalies in the Tables of Toledo, remaining the standard European ephemeris until the Prutenic tables almost 300 years later. 1408, Chinese ephemeris table, Chinese tables believed known to Regiomontanus. 1496, the Almanac Perpetuum of Abreu ben Samuel Zacuto. 1504, while shipwrecked on the island of Jamaica, Christopher Columbus successfully predicted a lunar eclipse for the natives, using the ephemeris of the German astronomer Regiomontanus. 1551, the Prutenic tables of Erasmus Reinhold were published based on Copernicus's theories. 1554, Johannes Stadius published Ephemerides Novae Auctii, the first major ephemeris computed according to Copernicus' heliocentric model, using parameters derived from the Prutenic tables. Although the Copernican model provided an elegant solution to the problem of computing apparent planetary positions. 1627, the Rudolphine tables of Johannes Kepler based on elliptical planetary motion became the new standard. 1679, La connaissance des temps au calendrier et éphémérides du livre en couche du soleil, de la lune and des autres planètes. First published by Jean Picard. Modern ephemeris. For scientific users, a modern planetary ephemeris comprises software that generates positions of planets and often of their satellites, asteroids, or comets, at virtually any time desired by the user. Typically, such ephemerides cover several centuries, past and future. The future ones can be covered because the field of celestial mechanics has developed several accurate theories. Nevertheless, there are secular phenomena which cannot adequately be considered by ephemerides. The greatest uncertainties in the positions of planets are caused by the perturbations of numerous asteroids, most of whose masses and orbits are poorly known, rendering their effect uncertain. Reflecting the continuing influx of new data and observations, NASA's Jet Propulsion Laboratory has to revise its published ephemerides at intervals of 20 years. Solar system ephemerides are essential for the navigation of spacecraft and for all kinds of space observations of the planets, their natural satellites, stars, and galaxies. Scientific ephemerides for sky observers mostly contain the positions of celestial bodies in right ascension and declination, because these coordinates are the most frequently used on star maps and telescopes. The equinox of the coordinate system must be given. It is, in nearly all cases, either the actual equinox, or that of one of the standard equinoxes, typically J2000.0, B19500, or J1900. Star maps almost always use one of the standard equinoxes. Scientific ephemerides often contain further useful data about the Moon, planet, asteroid, or comet beyond the pure coordinates in the sky, such as elongation to the Sun, brightness, distance, velocity, apparent diameter in the sky, phase angle, times of rise, transit, and set, etc. Ephemerides of the planet Saturn also sometimes contain the apparent inclination of its ring. An ephemeris is usually only correct for a particular location on the Earth. In many cases the differences are too small to matter, but for nearby asteroids or the Moon they can be quite important. Global Positioning System navigation satellites transmit electronic ephemeris data consisting of health and exact location data. A GPS receiver can use the transmissions from multiple such satellites to calculate its own location using trilateration. Other modern ephemerides recently created are the EPM, from the Russian Institute for Applied Astronomy of the Russian Academy of Sciences, and the INPOP by the French IMCCE. The Photographer's Ephemeris is a free useful software tool for photographers needing the times of twilight and the rise and set times of the Sun and Moon.